number one, it's easiest if you have a homogeneous fetch, a homogeneous space around your tower where you're measuring the flux, so that you can assign that flux to a group of plants that you know what they are. And it doesn't really tell you why the flux that you're measuring is the magnitude it is, right? It's a useful technique for quantifying those fluxes. But if you're interested in the mechanics, okay, what's happening at the level of the plant that's influencing this flux, that can be a difficult topic to address. So the last technique that I'll mention is modeling, right? A set of mathematical equations that describe our understanding of the system and that we can use to predict, say, emergent properties from that system. So we know something about what controls stomata: light, VPD, soil-water relations, and these other things that I've been talking about. Can we use that knowledge in a mathematical framework to say something about canopy level fluxes? So here's a paper that just describes a model. So, and modeling is very useful, right? Especially if you aren't afraid of a little math and a little computer code, stuff like that. You know? There's lots of people love that kind of stuff. so it can be very useful. And so what I want to talk about now is a very simple model to take what we know about leaf level stomatal conductance and scale that up to canopy level. And I say a simple model, okay? It brings to mind Einstein's famous quote, right? Everything should be made as simple as possible, but not simpler. That means, what do we know about stomata that is like the first thing that comes to mind when you think about stomatal conductance? What influences stomatal conductance? A big environmental factor. Light, okay? So let's forget about everything else and just think about light, right? Stomata are closed in the dark, open in the light. Can we use that knowledge to say something about water use by a plant? So it's kind of like we have to come to grips with the analogous term at the canopy level that we have at the leaf level, namely a canopy conductance for water vapor. So remember at the leaf, I had this transpiration was the total leaf conductance for water vapor times saturation at the leaf temperature minus the air open pressure, right? Well, we can use an analogous equation, right? So this is the total leaf conductance for water times the mole fraction water vapor difference. We can use that same approach at the canopy level and talk about canopy transpiration equal to this driving force, the difference in the water vapor concentrations, times a canopy conductance. It's sort of like the equivalent of the stomatal conductance, but for the entire canopy. And in this case, this canopy conductance term is in what is easiest, if we're interested in physiology, the units to deal with is in terms of moles of water vapor per meter squared of ground area per second. So we're going from leaf area to ground area because we're interested in all these leaves in the canopy. Okay. So we can do it. And quantifying this canopy conductance can be very useful for estimating water use because, for example, here's Penman-Monteith equation. Everybody knows this one, right? You remember from somewhere? Maybe. Some, maybe. Okay. Anyway, this shows the latent heat flux, or the transpiration in energy units, in terms of some environmental conditions. Here we have the net radiation that's above the canopy, the soil heat flux, so the difference between the net radiation, how much energy is coming in the top versus how much is going out the bottom, that's called the available energy. And that available energy is typically partitioned into sensible heat flux and latent heat flux. Here's the latent heat flux term. It depends on the aerodynamic conductance of the canopy, which is sort of similar to the boundary layer conductance, but now it's for an entire canopy, plant canopy. And you see some of these other terms, vapor pressure deficit. These are physical properties of the air. And this GS canopy, the canopy stomatal conductance term. Okay, so easy equation to use, is not very complicated. S is the slope of saturation vapor pressure versus temperature curve. This symbol is psychrometer constant. So here's the rho A is the density of dry air, CP specific heat capacity of air. You know, things that are easily measurable. Vapor pressure deficit determined at a reference height above the canopy. Aerodynamic conductance depends on the wind speed profile above the canopy, which is fairly easy to measure. You just put a series of anemometers above the canopy and you get the wind speed profile. So you can quantify this. But the real bear in this equation is, what do you use for canopy conductance? How do you know what the canopy stomatal conductance term is? It depends on light, it depends on VPD, it depends on how dry the soil is, all kinds of things. How do you do that? What I'd like to do is show a way of quantifying this term in terms of leaf level behavior, so that we can use it in an equation like this. And as I say, as simple as possible. So we'll just deal with light first, just light, nothing else. So I don't know if you're familiar with these energy fluxes for quantifying water fluxes, water vapor fluxes, but this transpiration rate, or sometimes it's you see it symbolized by a capital E, the evaporation from the canopy, or ET, evaporation plus transpiration. Regardless. Here I said this canopy conductance term is an appropriate unit would be moles of water vapor per meter squared of ground area per second. Right? This is the water use in energy units in watts per square meter. How do you convert from a molar unit or a mass unit, like let's say we have 500 grams of water per square meter per second. How do you convert that into an energy unit? Watts per square meter, which is joules per meter squared per second. Well, we have to use the here, in the way you usually see it in Penman-Monteith, this lambda E. E is the transpiration rate from the canopy in these units, in molar units or in mass units. And lambda is the latent heat of vaporization of water, which if you remember from the very first PowerPoint that I showed you, is 2,454 megajoules per kilogram at 20 degrees C. That's equal to as you can do a conversion yourself between mass and molar units, that's equal to 44.2 kilojoules per mole at 20 degrees C. So if we take this evaporation term, this transpiration term, in these molar units, multiply it by the latent heat of vaporization of water, we get units of kilojoules per meter squared per second. Or we can write it as joules per meter squared per second, or joules per second per meter squared, and a joule per second is a watt. So that's how you go from mass units to energy units, is you use this latent heat of vaporization of water. And usually, for some reason, in Penman-Monteith, it's explicit like this, lambda E. So I just did that. Okay, well, we know how to do that. Now, converting, so we should be conversant in energy units for water use. And we can also go for like units that a lot of engineers use or agronomists use, millimeters of water. You've heard of transpiration in, what's a high transpiration rate? A daily transpiration rate in millimeters of water. 7 millimeters of water. Pretty high rate. 10 is really good. 10 millimeters per day. What does that mean? That means for your canopy, it's using the equivalent of whatever the area of it is, it's transpiring 10 millimeters thick layer of water per day. That's a really high rate. In summer in Nebraska, 7, 8 millimeters a day is a pretty good transpiration rate. But we can also convert that because, a millimeter, if you take a millimeter of water over a square meter, that's a certain volume of water, a certain mass of water, and you can convert that to energy units the same way by multiplying by the appropriate latent heat of vaporization of water. So we can go from millimeters per day to moles per meter squared per day, moles per meter squared per second, watts per meter squared, any of these units. And they're all used for water use by different groups of people. So it behooves you, if you're interested in this, to be able to convert between these different ways of quantifying water use. All right, so let's get back to stomatal conductance. Here, let's focus not just on this canopy conductance. How are we going to do it? Light's arguably the most important environmental factor that influences stomata. Different leaves in the canopy and different parts of the leaves in the canopy have different exposures to light, right? Some of these leaves are lit up, some of these leaves are in the shade. This leaf will probably have a different stomatal conductance than this brightly lit leaf, just because this nonlinear conductance versus PAR curve. Right? The fact that this curve is nonlinear throws a little bit of a monkey wrench in it. If it were linear, this thing would be easy to do. If the response of stomata to light were linear, what we could do is measure how much light is being intercepted by the canopy. Spread that over the leaf area to get the amount of light per leaf area. Come on to our linear curve and say, aha, multiply by that, there, we got it. That's our stomatal conductance. But it's not linear. So the simplest way we can approach this is to split the canopy into two classes of leaves: sunlit leaves and shaded leaves. The sunlit leaves are going to be over here in this part of this. This is a leaf level stomatal conductance versus light curve. The sunlit leaves are going to be operating in this region. The shaded leaves are going to be operating in this region. So we've got to split that canopy into at least those two classes. The simplest, realistic way of dividing the leaf area. Here you see at the bottom of a maize canopy, these sunlit shaded parts of the canopy. We've got to take the leaf area in the canopy, and for our conditions, when we want to estimate water use, we're going to have to divide the total leaf area index, into sunlit leaf area index and shaded leaf area index. How can we do that?
use LAI measurements?
By,
LAI measurements, how much light gets in the soil, but in different,
yeah, I mean,
Parts of the canopy?
we can do the total. So the total is not too difficult to estimate the total leaf area in the canopy. But how do you know of that total that you measure, how much is in the sun, how much is in the shade? I think you're on the right track, because one thing we can take advantage of is the fact, what you just said, that some of the light gets through the canopy down to the soil,
Yeah.
right? I mean, let's pretend this is the soil down here. You know, you have sunflakes under the canopy. You've got patches of sun up there. So that sunlight is going all the way through the canopy down to the soil. It's not getting intercepted by a leaf on the way. And those patches of light and shadow vary throughout the day depending on where the sun is in the sky. As all can be used, hopefully. Let me start with this. This is small enough. Here we have an area, a blue area with a capital A, an area capital A. Let's superimpose on that, at random, some smaller area, alpha. Right? Now, let me stand back here at the back of the room with my cap in my hand. And if I throw this at the screen, I'm not gonna do it. I don't trust myself. Okay. I didn't even hit it. But assuming I can hit it somewhere in this area A, this blue spot, assuming I would have hit this blue spot, what's the probability that I can hit? And believe me, my throws are random, right? I'm randomly hitting this blue spot. What's the probability I hit that green smaller? Probability
I imagine it would be
hitting alpha, assuming I hit somewhere in that blue area.
it would be alpha divided by A.
Alpha divided by A, exactly right. Assuming it's at random.
oh, yeah.
Yeah, assuming it's at random, it's alpha, because I'm not trying to hit that. In my case, it doesn't matter, because I can't, even if I try, it's gonna be random.
Academics pays better than sports anyway.
Yeah. Okay, so the probability is alpha of A. So the probability that I miss, which is a much better probability, assuming I hit somewhere on the blue, the probability that I miss hitting that green spot is, assuming I hit somewhere on the blue, 1 minus alpha over A. That's a much better probability that I miss that small green area. Okay. 1 minus alpha over A. Okay, now, let's, okay, there we go. I used to use chalk, right, but now there's no chalk in there, I'm gonna have to use this pen. Okay, assuming the chalk hits somewhere, 1 minus alpha. Okay, now let's put another, same size of area, alpha, somewhere at random on here. And it's at random, it could overlap this, but most probably it's not gonna overlap. Okay, so we put another one. Now what's the probability that I miss both of them? Both of them. The probability that I miss both. Well, what's the probability I miss one? Is this. What's the probability if the areas are the same? What's the probability I miss the other one?
1 minus 2.
It's the same thing. So the probability I miss both is multiplied.
Oh, yeah.
So it's probability that I miss 2 of these is 1 minus alpha over A squared. Since if they're random, and I hit at random, that's about good. So if we have n of these little green areas, probability that I miss all n of them, 1 minus alpha over A, the nth power. Okay. That's the probability I miss all of them and I hit something blue. Now, if we have large enough n, large enough of these alpha, we could take the limit as alpha over a goes to 0 of 1 minus alpha over a to the nth, and that limit is e to the minus n alpha over a. So if I have a whole bunch of these things, in the limit, as alpha over a goes to 0, we wind up with the probability that I miss all n of these is e to the minus n alpha over a. And another way to write that, you know, is exp minus n. Right? That's the limit. If I have a whole bunch of these now, and they're pretty small compared to this large area, A, this blue area, represents the ground. These small green alphas represent leaves in the canopy. This limit, n times each area, leaf area, divided by the ground area, is the leaf area index of this canopy. So the limit of this is the probability that I miss e to the minus leaf area index. All right. So it's not surprising that the transmission through the canopy, in other words, the probability that I miss hitting any of these leaves, the transmittance through the canopy, it's not surprising that it depends on how much leaf area is in the canopy. Right? That makes perfect sense. But we've had some assumptions here. One assumption is that each of these leaf areas is in the same plane as the ground, right? Or not in the same plane, but at least parallel. It's horizontal, just like the ground is horizontal. We're assuming these areas A are horizontal. And that's not very realistic for a plant canopy. So, really, more realistically, we have some distribution of inclination angles of the leaves in the canopy. Some are horizontal, some are vertical, most of them are somewhere in between. So if we want to apply this transmittance equation to a whole canopy, to a more realistic canopy, the transmittance is exp to minus k of theta, this function, times the leaf area index. And this k of theta is called an extinction coefficient. And the value of that extinction coefficient depends on the distribution of the leaves in the canopy, the angular distribution of the leaves in the canopy. So, in words, this k of theta, so this is a function, right? K is a function of theta. What is theta? Theta is the angle at which I'm throwing this lid through the canopy. Or, if you're looking at a canopy, it's the view angle that you're looking at. And in fact, it's the angle relative to the zenith. So it's called the view zenith angle. So if I'm looking at a canopy like this, that view zenith angle is the direction I'm looking, the angle between that and going straight up from the point I'm looking at. If, on the other hand, we're talking about the sun, then this angle theta is what's called the solar zenith angle. Right, and so if the sun's directly overhead, that's 0. It's on the horizon 90 degrees. Or usually it's somewhere in between. Okay, so this extinction coefficient depends on that angle that we're looking through the canopy, or the sun is shining through the canopy, or I'm throwing my cap through the canopy. And K of theta is the normalized projection of the leaf area onto a horizontal surface. So in the simple example that we started with, this one, since these leaves are horizontal, the horizontal projection of that, the normalized horizontal projection of that area onto a horizontal surface is 1, because they're all horizontal. And that's why, if you have horizontal leaves, that K of theta is 1. It's implicit in this simpler form. Right, but typically that's not the case. There's very few canopies with horizontal leaves. Maybe you think of water lilies on a pond or something like that. Even that, if you look closely, those leaves aren't quite flat either. But you get the idea. Anyway, this K of theta is an extinction coefficient. Normalized projection of leaf area onto horizontal. Another common extinction coefficient that's used is usually symbolized as a G of theta. And that represents the normalized projection of the leaf area onto a surface perpendicular to the direction that you're looking, or the sun is shining, or I'm throwing my cap. That's called G of theta, and they're related by the cosine of the view zenith angle, or so on. So the transmittance through the canopy can be written as, in terms of this K of theta like this, or in terms of G of theta of minus K of theta times the leaf area index divided by cosine theta. And you may have come across this in your travels. I think that's the next slide. You may have come across this equation. You may have seen this before. Let's just look at this canopy though. Here we have an image that I find useful because this is a maize canopy, but the plants are small. If we're standing here in the field looking at our feet, we're going to see a lot of soil, right? The transmittance through the canopy is pretty big when we're looking straight down. But as we look at an angle, like way back here, you don't see any soil at all. Even with this really short canopy, you don't see any soil. So the transmittance through the canopy at a very large zenith angle is very small. So the direction you're looking at the canopy influences that transmittance. And here I mean transmittance, how much soil can you see compared to the total area you can see. So here, large transmittance, here small. So it depends on that angle that you look, or the sun is shining through the canopy. All right. We have to deal then with this extinction coefficient. And that depends on the arrangements of the leaves in space, and particularly the inclination angle, or the zenith angle of a normal to the leaf surface. All right. That's called the leaf angle distribution, that arrangement of leaves with respect to the vertical. It's called the leaf angle distribution. Well, with respect to azimuth too. But let's assume the azimuthal distribution is uniform. It is, we don't have to deal with it. It makes things complicated to introduce that. But let's keep it simple. Let's just deal with this inclination angle. And so there are different leaf angle distributions that are appropriate for different plant canopies. And the very common leaf angle distribution is what's called the spherical leaf angle distribution. So for a spherical leaf angle distribution, the value of this function k of theta is 1 over 2 cosine theta. The value for the spherical leaf angle distribution of g of theta is 1/2. So that may be why, if you have come across this transmittance through the canopy, it's oftentimes given, or you see it written as, the transmittance at an angle theta is e to the minus, what do I have for g? Oops, sorry. That's a g. K of theta. G of theta is 1/2. Yeah, that's why minus LAI over 2 cosine theta. This is a very common expression you'll see for transmittance through a canopy. What that assumes is the canopy has a spherical leaf angle distribution. What is a spherical leaf angle distribution? Imagine a sphere. You know what it is, a basketball or something. Take that surface of that sphere, cut it up into little bits, but keep it as a sphere, like a puzzle sphere, right? And each of those bits then, rearrange them at random in some volume. But don't change their orientation, just change their position, right? So if you got a flat bit at the top of the basketball, it's a flat, that bit stays flat when it gets rearranged. If you take all that surface area of the sphere, rearrange it at random in a volume, that's a spherical leaf angle distribution. And that's very common for plant canopies. In fact, maize, maize is very good example of a spherical leaf angle distribution. So, believe it or not, you take all these leaves, all this leaf area in this canopy, you could arrange it onto a sphere. Perfect sphere. I know. Can you believe it? Yeah, well, I mean, who would imagine that? Doesn't look anything like it. But, it is. Okay, so spherical leaf angle distribution, very common in plant canopies. And in fact, if you don't know anything, if you have a canopy, you don't know anything about the leaf angle distribution, assuming that it's spherical is not a bad assumption in many cases. But some plants aren't like that. Okay, so some are more horizontal, some are more vertical, although absolutely horizontal and absolutely vertical